Okay, in today's video, we'll be talking about the sprinkler hydraulic calculations. So the first thing is we're going to talk about discuss when the hydraulic calculations are required based on NFPA 13, 13R, and 13D requirements. And the NFPA is the National Fire Protection Association, and these are the codes that are followed for designing sprinkler systems. So these are the various different types, which I'll discuss when each of these different types are used later in this video. Then we'll discuss what is static and residual pressure in a hydraulic system. Then we'll explain pump curves and system curves and how to determine flow condition in a piping system. And then we'll go through an example of a sprinkler plan and perform the hydraulic calculations for the system and prepare the resulting report. All right, so first we're going to discuss the concepts basically, and then we're going to go through an example. So we'll discuss the NFPA sprinkler requirements now. For 13D, there are the sprinkler requirements for 1 and 2 family buildings only. All right, and for 13R, this extends to residential buildings up to 4 stories in height, and this means that it's everything other than 1 and 2 family buildings, as well as including 1 and 2 family buildings. So if you have a 3 family building, you would have to use 13R, and you can't use 13D. But if you had a 1 or 2 family building, you can use either 13D or 13R. And 13R is generally a little bit more, there's more requirements. So if you have a 1 and 2 family building, it's better to use a 13D since the requirements are a little bit less. Then you have NFPA 13, which is for all buildings, including these residential buildings here, as well as commercial buildings. So high-rise buildings, office buildings would all need to comply with this requirement right here, NFPA 13. Then you actually need to confirm with your local code, basically the local codes of the project you're working on, which NFPA code year version is to be followed, as well as if any modifications are made to that code, which then needs to be followed as the sprinkler code requirement. So, for example, in New York City, there is an Appendix Q in the New York City Building Code that contains the modifications as well as a version to be complied with. So, this would be the example of the New York City Building Code, Appendix Q, and this is a section in it. So, if you look here, you can see that it talks about the NFPA 13R, and it states the year that needs to be applied for the current codes for New York City, and in this case it's 2016 at the time of this video, and modified as follows. And this is just a small clip of that entire section, but there's an entire section that shows you what sections in the NFPA 13 code was modified. So in this case, you'll see section 1.1 of the NFPA 13R was modified in this way here, and you can read it. So in this example, it's delete after the word including and replace with the following: 6 stories in height in buildings not exceeding 60 feet in height above grade plane. So that means that this code, NFPA 13R, which if you look up here is for 4 stories in height, the New York City revised that section to state not only 4 but 6 stories. So you have to use a combination of these codes as well as any modifications that are made to it, and then you have to apply those codes to your project. So you have to check your local codes for something similar to the Appendix Q in New York City. So I basically took the 1.1 section in the NFPA 13R to basically show you what the actual section states in the NFPA 13R. So it says, this standard shall cover the design and installation of automatic sprinkler systems for protection against fire hazard in residential occupancies, okay, up to and including. So right here, the Appendix Q modified it. It says delete after the word including and replace with the following. So originally it said 4 stories in height in buildings not exceeding 60 feet in height above grade plane. Now that was crossed out, right, and replaced with 6 stories in height in buildings not exceeding 60 feet in height above grade plane. So you have to use these 2 code sections in combination. So we're going to first discuss the NFPA 13D hydraulic calculation requirements. So that part in New York City, it's handled by this section here in the Appendix Q. It's 103.1. And it basically just states, to follow the 2016 year edition, modified by this entire section here, which I'm not showing here, but you can find it. It's public information, and you could just search for it online. So the NFPA 13D 2016 Chapter 10, all right, gives the hydraulic calculation requirements, and there's a lot of different requirements in that section. I'm just going to list some of the main ones that I think are important. So you need a minimum discharge density out of the sprinkler of 0.05 GPM per square feet. So a standard residential sprinkler head, if this is the sprinkler head, is going to be a 12 by 12 box. So it's going to be 12 by 12. So from here to here would be 6 feet, and basically from here to here would be 6 feet right here. So this would be the coverage for the residential sprinkler head, and that's just the default coverage that you should apply when designing your sprinkler system to start off the design. If you look at the spec sheet, sometimes the coverage is a little bit more based on the pressure that is applied to the sprinkler head. But when you first design the sprinkler system, you should use this default coverage for residential heads of 12 feet by 12 feet, a box like this with the sprinkler in the center of it. So the maximum distance from a wall would basically be 6 feet. The second point is a maximum of 2 sprinkler heads in the design area that require the greatest hydraulic demand are the 2 heads that you have to calculate the hydraulic calculations to. So when you design the hydraulic calculation, you aren't designing so that all the sprinkler heads are activated in the entire building. You only need to design for the furthest 2 sprinkler heads, or generally the 2 sprinkler heads that require the greatest hydraulic demand. And usually those 2 heads are the ones that are at the highest elevation and the furthest from the source. It doesn't necessarily mean that it has to be at the highest elevation. The most demanding sprinkler heads can actually be something that's not at the highest elevation, but generally it is at the highest elevation and the furthest from the source of water. You also have to design it so the minimum operating pressure of the sprinkler, all right, is based on the specs or 7 psi. Okay, so the higher of the 2 of these requirements is what you have to design the hydraulic calculations for. And I'll explain this a little bit further later on. Number of design sprinklers. So this is just one section I pulled out from NFPA 13D. For each of the following situations, the number of sprinklers in the design area shall be all of the sprinklers within a compartment, up to a maximum of 2 sprinklers that require the greatest hydraulic demand. Compartment just means like a separate room, or a fire area would be a compartment. So it's going to be, according to this section, all the sprinklers within the compartment up to a maximum of 2. So, if you had 4 here, you would basically use the furthest 2 sprinkler heads in your hydraulic calculation. For example, if it was something like this and the water was coming this way, these would probably be the furthest 2 sprinkler heads that you would use in your hydraulic calculations. Let's say the compartment only had 1 sprinkler head, and let's say you had another sprinkler head in another compartment over here. In this case, I would still use the furthest 2 sprinkler heads in the hydraulic calculation, just because I'd rather have it designed for 2 rather than just 1. So even though the code states that it can be even though the code just states that the design area shall be all of the sprinklers within a compartment, so in this case, if there's 1, you could just do it for 1. I would still design the hydraulic calculations for 2, since I prefer to add a little bit of safety to the design and include 2 sprinklers instead of just 1. So this is a standard spec sheet on a residential sprinkler head that you see right here. And this is basically the model number. It's the residential concealed pendant sprinkler, and this is the model number, and there's a K factor here. All right, the K factor basically is just a number that could be used to determine the GPM that will be flowing out of this sprinkler head based on the pressure provided to the sprinkler head, which I will explain later in this video. So for residential systems that follow basically NFPA 13D or 13R, you need to use these residential sprinkler heads, which are different from standard sprinkler heads that you generally use in commercial locations. For NFPA 13D and 13R, we select these residential sprinkler heads to use. And if you look at this schedule right here, you will see that there are different ranges of throw that the sprinkler covers. So here is a 12 by 12, 14 by 14, and these are in feet, as you can see here, and the ones in parentheses are in meters. I'm going to use feet since I'm the US and we use units of feet. And you could see that these are the ratings based on a specific pressure provided to the sprinkler head. And for that pressure, you get a certain flow rate here. Okay, so you could see as the pressure goes up, you have basically more GPM and a higher throw. So it goes further based on the pressure. So in this slide here, I mentioned that the minimum operating pressure is based on spec or 7 psi. So if the spec states that we need 7.6 psi here for the standard lowest throw, which is 12 feet by 12 feet for a residential sprinkler head, then we would use this as the minimum pressure requirements in our hydraulic calculation. Now, if this said 7, we would use 7. And I have never seen anything less than 7. So I've never seen something that stated 6 psi for residential. But let's say it was 6 psi. Then we would have to use the higher of the 2 minimum and go with the 7 psi. Because here it shows that minimum operating pressure is based on specs or 7 psi, and it's going to be whichever is larger. So here, if it was 6, we would use the 7, since 7 would be the larger or the higher psi requirement. In this case, it's 7.6 is the larger of 7 and 7.6, so we would use the 7.6 psi into our hydraulic calculations in this example to get this minimum throw that we need. In certain situations, you might want to get a bigger throw because the room that the sprinkler is in may be a 14 by 14, So in that case, we would have to use this 8.6 psi into our hydraulic calculations. So it all depends on what type of throw you need, but the default, so what you begin with is this minimum 12 by 12 foot throw. And depending on your job and if you need a higher throw, then you would use a different value into your hydraulic calculations if you need to, based on that sprinkler head, if it happens to be the one that requires the most hydraulic demand, okay, which generally is the highest and furthest away from the source, but not necessarily. And when I state the most demanding sprinkler head hydraulically, does not necessarily mean it's at the highest and furthest point. I'm going to try to demonstrate in this example here. So we have a water service that comes in this way. It goes up. This is the elevation. So let's say that these are the floors, and this is the top floor that it's on. And this is the sprinkler head, and this is a sprinkler head on a lower floor. This height elevation, let's say you lose 4 psi, that goes basically from this point here to this point, and then you have 1 psi of friction loss in the piping. So the total loss from this point here to the sprinkler is going to be 4 plus 1 psi, so you have a 5 psi loss. Let's say this sprinkler head, which is at a lower elevation, you basically have 4 psi more at this point than at this point because of the height elevation. So let's say, I'm just going to make up a number. Let's say this is 50 psi pressure. The point right here would be 4 more than that, right? So you have 54 psi of pressure right here. And the friction loss in this piping length is going to be 10 psi due to the water flow to this sprinkler head here. So your final losses is 54 minus 10. So your pressure here is going to be 44 psi. And your pressure here at this sprinkler head is going to be the 50 psi minus the 1 psi of loss. So it's going to be 49 psi of pressure right here at this sprinkler head. So looking at this system right here, you could see that this sprinkler head is at a psi that is 5 higher than this sprinkler head, right? 5 higher, 44 and 49. So let's say that the requirement of this sprinkler head was 7 psi. Okay, that means that since it's 5 psi different, if this was 7 psi, okay, this sprinkler head, then this would be 5 less, right, in the system. So it's going to be 2 psi here. And as you can tell in this example, that this one right here would be the most hydraulically demanding sprinkler head that you would have to use for your hydraulic calculations. And that is because as long as this one is getting the proper pressure, you know that the other heads in the system will get more than the minimum that is required, right? Because if you have, let's say, 7 psi here, which is the minimum required, let's say for this one, then you know that this one will be 5 psi higher. So you would get 12 psi at this sprinkler head, and then this one would be getting the minimum pressure requirement for that head. So therefore this is going to be the most hydraulically demanding sprinkler head, because as long as you comply and provide the pressure required for this one, all the other sprinkler heads will get the minimum pressure it needs. Changing this example up just a little bit, let's say instead of the 10 psi right here. Let's say instead of the 10 psi here, this was, let's say, 5 psi. So let's say instead of this, you have 5 psi here. So the drop would be 54 minus 5, and this will be 49 in that case, right? So the difference in pressure between these two sprinkler heads are exactly the same, right? It's 49, 49. So if it was 40 psi, then this would also be 40. So whatever psi this sprinkler head is at, it'll basically match this sprinkler head. So if you need a minimum of, let's say, 7.6 psi for both of them, that means that either one can be considered the most demanding sprinkler head that would be used in your hydraulic calculations. But let's say this sprinkler head here was for a large room that was 20 by 20, and you needed this sprinkler head to throw that 20 by 20. Then you need a minimum pressure of 11.9 at this sprinkler head here. So in that case, this one would be the most hydraulically demanding sprinkler head that you would use, because it has, so basically it's the difference between 11.9 and 7.6. So you have a difference of 4.3 psi difference. So in that case, this would be the most demanding one you would use in your hydraulic calculation, because if you set this one to meet 1.9 psi requirement and the pressure is the same, right? There's no difference in pressure in this case, showing at 49, 49, but whatever psi it is, it's going to match in this system. So if we need 11.9, then this sprinkler head here, right, would be 11.9 as well, which then would be more than the minimum required for this sprinkler head, which is going to be this 7.6. So in that case, this one would be the most hydraulically demanding sprinkler head. So this is a very long way of stating that it's not always necessarily the case that the highest sprinkler head that is furthest on that floor level or that height level is going to be the most hydraulically demanding sprinkler head. There are cases where that may not be the case, and that's what I'm trying to demonstrate in this example that I just showed you. But most of the time, usually the sprinkler at the highest elevation and the furthest at that elevation is going to be the most hydraulically demanding sprinkler head. All right, I want to explain how this concealed pendant works. So this white cover right here is actually flush to the ceiling. So the ceiling would be right here, and if you look here, there's two metal rods here that actually slide up. So this piece right here would actually slide up this way, right? So this deflector piece here would slide up, and the white cover would actually go right here. So when there's a fire, it basically melts the solder, the fusible link. That's basically holding up this cap. This cap will fall off, and then this deflector would basically slide down, which would then allow the water to hit it and basically spread along the bottom of the ceiling. So that's generally how this concealed pendant works. So now I'm going to talk about the NFPA 13R, and this is the New York City Building Code Appendix Q, Section 104. So here they state which version to use, which is the 2016 edition. So it's important to know which version that is relevant, so you're following the correct version before you even begin any job and trying to see what codes to follow. You have to confirm the proper version of that code. And NFPA 13R Chapter 7 is what gives the hydraulic calculation requirements. All right, so this is the snippet of Chapter 7 in the NFPA 13R. And here it says the minimum discharge density is 0.05 GPM, right here, per square feet. So it's same as the NFP 13D requirement for the density. The difference here is you need a maximum of 4 sprinklers in the design area that require the greatest hydraulic demand, whereas in 13D it was not 4, it was the 2 that required the greatest hydraulic demand. And the minimum operating pressure of a sprinkler is, again, based on specs or 7 psi. So this pressure requirement is the same for 13D and 13R. And the section that talks about the 4 sprinkler heads is right here. And right here it says it's a maximum of 4 sprinklers that require the greatest hydraulic demand are the sprinklers that are used in the hydraulic calculations. Okay, now we're going to talk about the NFPA 13 requirements for hydraulic calculations. So NFPA 13, it doesn't use the furthest or the most demanding 2 or 4 sprinkler heads, but the way NFPA 13 works is you have to apply a density for all the sprinklers within a certain area. So this is the density area curve, and based on the type of occupancies, whether it's light, ordinary, or ordinary 2, extra hazard, or extra hazard group 2, you use different densities based on the area that you're applying the hydraulic calculations to. So if the area is 1,500 square feet, you apply 0.1 in this case, 0.15 in this case, GPMs per square feet. So if you're applying it to a higher area, then you would use less of a density for that area that you see here. And most of the time we use this area here. So the most remote 1,500 square feet is what I typically design the calculations to, and it's what most hydraulic calculations are performed with. So it's the most remote 1,500 square feet, and depending on the occupancy type, you would apply that density to it. Okay, and this table right here gives you a hose stream allowance that you also would have to add on to that density area requirement if you have a hose. And you can either use 0, 50, or 100 based on what the code requires for your particular job. If you do require a hose, some jobs you may not need to install a hose system. And there's also different durations here, 30, and there's 60 or 90, and 90 and 120. So the code explains when the lower values are used, and it's in this section right here of NFPA 13. It says lower duration values in that table shall be permitted where sprinkler system water flow alarm devices and supervisory devices are electrically supervised, and such supervision is monitored at a approved constantly attended location. So basically all of this is what's on the fire alarm system. So if you have a fire alarm system that is constantly monitored by a central station, then you could use the lower duration value here. And if your sprinkler system is attached to a city water supply, you wouldn't really be concerned with the duration. But in some cases, you have the sprinkler system coming from a water tank that is located generally on the roof. And in that case, you would have to get the correct gallon size for that roof tank in order to meet this minimum duration right here. But again, if it's connected to the street supply, then you wouldn't really need to concern yourself over these minimum duration times. So let's look at an example of an NFPA 13 job. So let's say you have a sprinkler system like this. So the water supply comes in from this side, and these are the heads, okay, that you see here. Let's say that this is a light hazard occupancy. So to determine that, you have to look at the NFPA 13 hazard group section, which is in Annex A, and it'll list the building types that correspond to these hazard occupancies. So for a light hazard, you would have all these building types included in that category. And most things fall under this category, light hazard occupancy, because most of the jobs that are done are in, education, residential, as well as offices. Now, if you look here, ordinary hazard group one, these are the building types that fall under that category. So if you have something such as laundries, bakeries, electronic plants, they would fall under this. So you would follow Annex A to first determine what type of hazard group you are in. And then once you determine the hazard group, in this example here, I'll state that this is in a light hazard group. So we follow this right here, this graph, and we're gonna use the 1500 square feet at, so 1500, it'll be basically 0.1 GPM per square feet. So you would take the most remote 1500 square feet. So that's the furthest point generally from the source, which is going to be most likely, this section right here. So you would basically take this, if this was, 1500 square feet at least, this would be your design area right here. So you would have to design your hydraulic calculations, assuming that all of these sprinkler heads within that most remote 1500 square feet area are activated. So then you would basically use all of these heads in this zone as part of your hydraulic calculations and use a minimum of 7 psi as the minimum pressure required for all the sprinkler heads. And you would use a density of zero point 0.1 GPM per square feet for each of the sprinkler heads within that zone. Basically applied to the spacing of that sprinkler head. And for NFPA 13, the standard default spacing with the sprinkler in the center would be 15 by 15. So, with the sprinkler head is basically in the center of that square. And the area then would be 15 times 15, which is 225 square feet. You would apply that density of 0.1 GPM per square feet to that area for each of the sprinkler heads. So in this case, the 0.1 times 225 would be 22.5 GPM per head is what you would basically use as part of your hydraulic calculation. Just to clear up the terms a bit, just to give more clarity, when I refer to the static pressure that is in the hydrant flow test, it's actually the static pressure at zero flow conditions. And when I refer to the residual pressure from the hydrant flow test, that just means that it's the static pressure at a specific GPM. And in most cases, that's 500 GPM for hydrant flow tests. So the static pressure would just be that pressure that pushes against the walls of the pipe. And at zero flow, the static pressure would be much higher. And with flow, the static pressure would basically drop since you're basically splitting up that total pressure to the velocity pressure.